So I'm currently building up my own 8-bit Superscalar out-of-order processor, and this is its current state. As you can see, it's already doing something. It can execute simple programs that are stored here in the program memory. It has a program counter that steps through the individual instructions here and then basically executes it. And they're not really complicated. We can jump around the memory a bit, and we have two registers here that we can play around with. And as we can see, there's a pattern here showing up. But two registers isn't really all that interesting. It's not enough to do any kind of complicated computation. To allow us to have more than just the two registers we have here, in the last episodes we were busy building up this register PCB here, which is basically one of these registers, R0 or R1, put onto a PCB. And so what I want to do today is replace the two breadboard-based registers we have here with some of these PCBs that we've built in the last episode. That's going to give us a lot more registers to play with, and that's going to make the processor a lot more powerful. These are the four register PCBs we have assembled and tested the last time. Let's now assemble them into a full register file. I've gone ahead and soldered up a stripboard PCB with a lot of sockets that we can plug these register PCBs into. And all this is basically a PCB that has vertical traces that connects all the pins vertically. And so what we can do here is if we take one of these GPRs and plug them in here, and take another one and plug them in down here, all the pins at the bottom here of the PCB get connected vertically into one big bus. So all the write data, read data 1, 2, and 3 ports, the power, and the clock gets connected vertically. And since we have some room left down here, I added more of these sockets here. And I also went ahead and soldered up 3 more of these PCBs, because that's all we can fit onto this stack. And so down here, there's a header that we can plug wires into that connect to the different buses that run vertically here. So that's going to be our way to access whatever comes out of the registers and also to drive the write data bus. Now we also have some control connections here on the side. This is basically the signals that enable the writing into a register, and also that select which register gets to put its data onto the read data 1, 2, and 3 bus. And so we need to somehow break them out as well so we can hook up a wire to them. And I think we'll just use these header breakout connectors here. These are leftovers from the program counter work. Basically, it's just 2 headers that have the corresponding pins connected. So let's wire this up. All right, that's pretty neat. So at the bottom here, we have the data bus connections and power and ground and the clock. And then on the side here, we have the control connections to select the individual registers for reading and writing. And in the future, we'll build up a proper backplane that has all of these connections on a separate PCB, and we can just plug in these boards, but not today. This is going to suffice for what we're doing today. So each of these PCBs here that we plugged in, they correspond to one of these register breadboards, the R0 here, for example. But we need also a way to control these write enable and read enable signals for every individual register, which is basically going to control the individual chips here. On the breadboard, we've used these 74HC139 chips. These are 2 to 4 decoders, which are really useful. They have 4 output wires, and what they do is they take a 2-bit input number, and then they're going to select one of those 4 output wires, the one that corresponds to this number. And so this is a very neat scheme to take a number as an address and turn it into a long list of select signals where only one of those select signals is ever going to be high. Now we've expanded to 7 registers in total, so this isn't going to fit anymore. But there's a similar chip, the 74HC138, which is a 3 to 8 decoder, so it's basically twice the size. And I think that's what we're going to use for the registers over here. It takes a 3-bit number, which is going to select one of the registers, and it's going to produce 8 different select wires, which we can directly hook up to write enable or the read enables. In the future, we might want to expand to even more registers, say 16. There's clever ways how you can use these 2 to 4 and 3 to 8 decoders to actually expand to a fairly large number of select lines that you can toggle. But that's a topic for the future when we actually do that expansion. For today, we'll just do a similar scheme as we did with these decoders here and basically add a companion breadboard to the new register stack that controls all of the signals. So let me move this out of the way again. All right, so we'll be adding such a companion breadboard here to the side. Let's connect the power rails. We'll also want some decoupling capacitors. So let me dig up the 74HC138 chip that we are going to use. So let's take a look at one of those chips here. They have their select output signals all at the top here and one kind of around the corner here at the bottom. And at the bottom here there's the 3 input select wires which basically select one of the 8 outputs and some enable signals that we'll use or not use, we'll see. And so I think it makes sense to rotate these chips around this way such that the select outputs are on the right hand side where they're pretty close to the select inputs of the registers. Let me connect the power and ground pins. All right, then next up, here on the left-hand side, basically the bottom side of the chip, there's 3 enable inputs. There's a G0, G1, and G2. And G0 and G1 are active low, so we'll want to tie them to ground to have this thing enabled. And G2 is active high, so that we want to connect to VDD such that the chip is enabled. All right, so that's all the enable inputs connected in a way such that hopefully they enable all of these chips. And then the first 3 inputs here in the top left, these are the actual select inputs. These are going to select one of the outputs. For now, let's just tie them to ground such that they have a defined input potential. All right, so that's all the select inputs at 0. And what this will do is it's going to enable the very first output in the top right, the output number 0. So what's left to do now is connect the select outputs of the chips to the select inputs here on the registers. And so we'll do this as follows. The first chip is going to drive the write enables. The second chip is going to drive the read enables of the first read port. And the third chip is going to drive the read enables of the second read port here. And then the third read port we're currently not using at the moment, so we'll just connect all the read enables of that port to a 0, but we'll come up with a better way to use this port in the future, but not today. So the topmost pin here is power, then is output 0, which we're going to skip like we did on the breadboards, such that selecting address 0 just means not selecting any register. And then output 1 here is going to go to the write enable of the first register. So that's the write enables done. Let's continue to the read enables for the first port. And let's continue with the second read port. All right, so that's the write port and the first 2 read ports connected. We don't have a chip for the third read port here. And since we're not using it at the moment, let's just connect the enable inputs for the third read port to VDD to disable them. These are inverted inputs, so they're active low. Let me also hook up ground up here so we have a good ground connection to the breadboard. I think we'll want to give this a quick try and see if we can select the right registers with the address inputs here. And for that we need to connect the power of this stack here over to the breadboard. So there's a ground connection here and a VDD connection right next to it. We'll just bring this over like so. Pretty neat. And then the rest of the connections are made by the strip board here in the background. Let me power this up and let's give it a shot. Just now realized that I forgot to cross-connect the power rails here. It's one of the breadboard types that has the power rails disconnected. So let me quickly patch those over. Okay, much better. So let's give this a try. All right, so the registers power up and they contain the usual random garbage in them when we power them up. So what I should be able to do now is use the write address here, which is basically the select signal for the first chip, which is then going to drive one of the write enables in the stack here. I should be able to select a register number and then the corresponding registers, the light here should light up. That's a 1 at the input, which selects register number 1 up here. That's a 2, which selects register 2. A 3 selects register 3. A 4 selects register number 4. Number 5, 5th register. Number 6, the 6th register. Number 7, the 7th register. So that seems to be working. It's pretty cool. Let me reset that back to 0. Now let's try the same thing with the second input number here, which is controlling the second chip, which in turn controls the first read data port. So 1 selects the first register on read data port 1. That's a 2, register 2. A 3, register 3. A 4 selects register number 4. 5, number 5. That's a 6, register 6. And a 7, selecting register number 7. Pretty cool, that seems to be working. And then as a final test, let's do the exact same thing for the second read data port, which is controlled by the third chip down here, which is controlled by this select input. So number 1 makes the first register light up. Number 2, second register. 3, third register. 4, fourth register. 5, fifth register. 6, sixth register. And 7, seventh register. Pretty cool. So by setting these input numbers here, which are basically the register address if you want, the number that corresponds to the register, we can make the corresponding control signals here light up. So write enables and read enables, pretty much the same way as it worked on the breadboard, but now instead of just 2 measly registers, we have 7 in total. This is going to be pretty useful for more complex programs in the future. And just as a sanity check, none of the third read port enables light up because we tied all the control signals to their inactive voltage, which is VDD. So they're disabled. But if we were, for example, at the last register here, gonna pull the read enable line low for the third read port, we can actually see that that lights up. But we have no control logic yet to drive that, and we'll get to that in the future. So let's just disable them for now. So before we bring this over to the CPU build and integrate it, remember that the old register file had a bunch of LEDs at the top that basically showed us what the write data and all the read data ports were currently carrying as a value. And I think we want to have the same thing here with this register file. So it's easy to kind of inspect what data goes into the register file and what comes out of it. So let's add another breadboard down here with just these LEDs for now, such that it's easy to observe. And we basically have one unit that we can integrate into the existing CPU. So let's use some of these LEDs again. And so we'll bring the data wires from the top here down to this breadboard and then connect them to the LEDs. And let me also hook up the power connections here. We'll also want to connect the power rails of these two breadboards. And then we'll also want to connect the power rails of this breadboard here. Then we can place the LEDs. And the LEDs need a resistor. And we want the resistor to be towards ground. And let me also add some decoupling here. It's not really necessary, but since we have so many power connections here across breadboards, it might help stabilize power a bit. So that should be our new register file. 7 registers here. We have some addressing logic here with 3 separate register address inputs, 3 bits each, to select a number between 0 and 7. 0 being no register at all, and then the numbers 1 to 7 correspond to the registers. And then at the bottom we have a new bus data monitoring thing, if you want, which basically just shows what's on the read and write data buses. Let me power it up quickly once again to see if these LEDs work. Okay, powers up in this random state. And now we should be able to select one of the registers on the read data port 1 and see its output down here on read data port 1. So register 1 is selected. And indeed, the number here, basically all bits set except the lower 2, shows up here at the readout LEDs. And then similarly, on read data port 2, we should be able to select a register. Register 4 in this case, which has all the bits set, and indeed that's what shows up down here on the read data port 2. And then the third read port, we don't really have an address selected, but we can just forcefully select one of the registers that we have. For example, this one here. So that's register number 7, and that's enabled now. And as you can see, the value it has shows up here at the output. And then let's quickly check the write data port here. And yeah, that seems to be working. That shows the same number as the read data port 1. So the LED seems to be working, the registers seem to be working, the select lines seem to be working, which means that this decoding logic here is also working. So I think it's time to actually bring this back over to the actual CPU build and integrate it there. And let's see if we can run the existing program without any modifications. All right, so basically what we have here on the left is a replacement for this side here of the processor, basically the register file. It's using a fair amount of space because we have this discrete select logic here on the side and this readout bus here. But the register file is almost fully functional the way it is. And in the future, if we think about making a backplane for this, such that there's kind of a convenient way to mount this somewhere, we could put some of the select logic onto the backplane or onto a small PCB at the top here to make this a lot more neat and convenient to use. And then it's also going to be a lot smaller. But it's pretty good already. This is 2 registers. That's a total of 7 registers plus a 3rd read port, where this breadboard version only had 2 read ports. So we're making good progress here, and I think it's time to integrate this over there. So first up, let's actually lose some of these connections here that go all across the thing. One of them is this clock line here, which we can temporarily take from the original source up here. Then this is the clock connection to the program counter. This we can disconnect for just a second. And then this here is the clock wire coming over from the clock generator. Power we can disconnect. This yellow line here is the read enable for the 2nd read port, and we use this to select between an immediate value coming from the instruction bits and the register value coming from the register file. And we'll need a replacement for this as we go on. So we'll disconnect this for now. And we'll want to remove the top 3 breadboards, which are the actual register file. But we'll want to hold on to this immediate buffer that we have down here, which is basically currently just doing the forwarding of immediate values onto the register ports. But this is useful, and we'll expand on this in the future. So this one we'll keep. This stuff at the top we'll disconnect. So let me first lose these connections here. Let's see if we can split this apart. So there's a few more connections here that we need to take care of. First of all, there's this connection to the relative jump offset over here. So we'll have to lose that. We'll see what we can do with it. Let's move this aside. Then there's the absolute jump address here. This will be able to pick up from the new register file. So that's our 2 register file, which we've now replaced. So that can go away, and we'll bring in the new one and hook everything up. It's quite a bit bigger. So I think what we want to do is this immediate buffer down here that was below the register file until now. I think we want to bring it over and place it underneath the program memory here, which is basically where it belongs, because all this does is it takes a piece of the instruction that's coming out of the program memory and pushes it onto the read data port. So that's a good location to put it. So I think we want to combine the power rails here, such this is one thing. I think we can shorten this cable here. This is the bit of the instruction that selects whether we're using the immediate bits or a register output. Okay, so first things first, we'll need a power connection here between these 2 things. This cable here is the connection between the write data port and the read data port 2. And what this did basically was it allowed us to either take one register's value and store it into another register, or take the immediate bits that are in the instruction up here and store those into a register. And in the future, we don't want this to be a direct connection, because there's other ways we can store stuff in a register, for example, the result of a computation. But for the time being, this suffices. I think we'll just want to bring this over to this new breadboard. And then instead of using the breadboard to make the connection, there's actually a pin header up here that we can use to connect to these ports as well. That's going to be useful for some of these wires, like this cable up here that's coming from the relative jump offset, because we can essentially just plug this in from the top here. And either we do this or we use the top connection here for the forwarding path from RD2 to the right data port. I think that's what we're going to use it for. What else do we have here? We have this relative jump offset here, which was also connected to RD2. So we want to bring this here to RD2. But I think we can do it via this buffer here, which is also where RD2 is going to need to be connected. And then we have the absolute address over here. This one we're also taking from the RD2 port. So I think what we want to do is take this and connect it to the same position of the breadboard here. Let me use a better cable for that. And then finally, we actually need to take this RD2 connection here and bring it over to the RD2 port. All right, so that's RD2 connected up. What else is missing? We have this clock wire here that we disconnected. This was going from the clock output of the clock generator here all the way over to the register file. And indeed, the register file has a clock input that we're currently not connecting to. So this will need fixing. I think a neat way to do this is to use one of these power rail strips from one of the breadboards and just jog it in here in the middle. We can connect the clock over here, and we basically have this rail in the middle that we can use to grab the clock where we need it. For example, the program counter here needs the clock, so that can go here. The program counter also needs the reset. We can put this onto the rail here as well. And then down here we also have a clock connection. This one is coming directly from the clock module and goes into the latch here, but I think we also want to take this from the clock and reset rail here. That's quite a long cable. I think we can replace this with something shorter. And then finally we have the clock input of the register file over here, which we also need to connect. And down here at the immediate buffer, we have this control wire here. This is connected to one of the bits of the instruction, the bit that selects whether we want to use the immediate bits as the second operand, or we want to use the RD2 result from the register file as the second operand. And this wire, when it goes high, we want to use the immediate bits and drive them onto the RD2 bus. And so we've been using this wire here to enable the read data port of the register file to disable it when we use the immediate bits. So we need to establish the connection from here to the select chips, which is where we use to implement this enable. And so the chip in question is the third one down here, which is controlling RD2 reading. And if you recall, it has 3 enable inputs, and we connected them to their active state. But what we can do now is we can remove one of these connections to ground and instead connect the enable input to the immediate buffer over here, such that we can disable reading from RD2 whenever the immediate buffer wants to drive a value. And so the final thing we need to deal with is the register address connections that come from the instruction bits. These we need to bring over to these register select lines that we have over here. Let me use some longer wires for this. First up, this is the first register operand. This is the RD operand, which we used to indicate the destination register where we want to write to. And then there's the second register operand. This is the RS register, the source register, which is what we've been using to read the second read port. Okay, and so in terms of connection, we want to connect the RS, the source register, to read data port 2. And we have the RD operand, the destination register. This we want to connect to the write data address. And now, if you recall, on the breadboard version of the register file, we actually cross-connected the address for the write data port and the first read data port, such that whichever register we write, we also get read out on the first data port. And I think we want to do the same thing again. All right, so this looks pretty complete now. I think we should just be able to run the existing program that is still in the program memory from last time. If you recall, that used the first two registers to jump around the program a bit and to show a pattern on the first register here. We've changed the register file around and we have a lot more registers, but it's basically going to address registers 0 and 1. This will just work as it is right now. So let's give this a shot before we make any changes to the program. So it's in reset. Let me step it out of reset. 1, 2, 3, 4. So this is kind of the starting configuration. There's just some random stuff in the registers, and we are at address 0 in the program, and we're ready to execute. And so if you recall, the program, what it does is it first clears the first two registers. Okay, so on the first clock, it wrote a 0 into the first register. Doesn't change anything because it was already 0. But now the next instruction is a move from register 0 to register 1. And indeed you can see we're reading this register and we're writing this register. So if I hit the clock, the data gets copied down into R1. And now we're doing an absolute jump. And now we're loading two different values again into the first two registers. And indeed, those were the values we had in the program, just some different patterns. And then we're going to load the binary value for 6 into this register, and then we're going to use it for a jump. So that's the 6. And here you can see the select line of the program counter going on because we're doing the jump based on this offset. That had us jump to a different location. And now here we're loading hex 40 into register 0, which is basically the immediate bits here in the instruction. So that's hex 40. And then we're doing an absolute jump to that address. So we are going to see this value being copied into the program counter. And that's exactly what happens. And now we're in this endless loop we had going the last time, where there's just a walking bit pattern here. So if I hit run, we should see that. And there you go. All right, so the good news is the new registers, at least the first two work, and we didn't break anything about the processor when we made these changes. So I think now is a good time to actually go back into the program and make a few tweaks to the assembly to actually use more of these registers as a kind of demonstration. All right, so let's take a look at what the current program is that we're running on the CPU. So we have this instruction set architecture document, which is summarizing the instruction encoding and also contains our sample program down here. And so up until this point, we just loaded register R0 with the value 0, and then we copied R0 into R1, which basically cleared the two registers that we had. But now we've upgraded to 7 registers, so let's add a few more move instructions to clear all of them as well. So as a second step, after R0 and R1 are cleared, let's copy R1 into R2, R2 into R3, R3 into R4, R4 into R5, and R5 into R6. So let's update this instruction encoding while we're at it. Now let's actually move this code block a bit further down in the program. So let's make it start at address hex 20. And so here the absolute jump we want to change to jump to this hex 20 address as well. This isn't really needed, but it's just nice to keep things a bit separate. All right, and then down here, this was the part where we loaded different patterns into the registers that we have. And I think we just want to add a few more patterns to be loaded into all the other registers that we've just added, such that we have something interesting to look at. So let's think what we can load into these registers. Maybe R2 could be the opposite of R1. That's AA, that's just all the other LEDs turned on. Register R3, we could do 0F, which is the opposite of R0. 81 should be an interesting pattern, which is the first and the last bit set. And 42, which is the second to last and the second bit set. And then finally, let's just turn on all LEDs in register 6. All right, and let's update the encoding while we're at it. And then the number here in front is the value we are writing into that register. So let's copy that. And then I think this relative jump that we're doing through register R0 will just keep as it is. That was pretty okay. This should all stay the same. That looks good. And then we're down here in this loop where we're basically just looping over this snippet of code which created this marching bit pattern in register R0. And I think now that we have more registers, we want a similar pattern, but let's actually spread it out across all the registers that we have. And then this last step, we have no more register to put this in, so let's just turn this into a knob for simplicity's sake. And then the second half of the pattern is basically the bits walking backwards. And again, we'll just spread it across all the registers we have now. And then this final instruction, again, we have no more register to put this one into, so let's just turn this into a knob. All right, so what this will do is register R0 will have its first bit set, register R1 its second bit, R2 its third bit, R3 its fourth bit, and so on. And then once we're down here and all the registers have been set, we go back to register R0 and set its last bit. Then we go to R1, set its second to last bit, R2, third to last, and so on until we're through again. And then we just loop around and we keep iterating. That looks pretty good. Let's update the encoding. First of all, the knobs here. And then we have to update this column of numbers here, which corresponds to the destination register where we're storing the value into. And we've changed this for all these instructions. So register R1 is address 2, R2 is address 3, and so on. Same thing down here. So I think it's time to assemble this. All right, so that's the bytes at the different addresses that we need to write into the hex file. But if we take a look at the hex file itself, you can see it's always 8 bytes in a row, and then we continue on the next line. So let's add some line breaks. So we'll make it easier to copy things around. So that's 4 bytes. That's 8 bytes. So we add a line break there. Then we continue down here. And then for simplicity's sake, let's fill up the remaining bytes here with the zeros. It's going to make copying a lot easier. All right, so let's copy this into the program memory. So here's the hex file of the program memory. So we can just grab these blocks of data and we will just paste them in here. Then at address hex 20, that is down here, we want this block of 4 lines. And then at address hex 40, which is right here, we want this block of 5 lines. Let's convert this hexadecimal file back to the binary file that we can actually program onto the chip. All right, so let's write this binary program into the program memory. All right, let's give this a try. All right, let's step through this program and see if it works. We're in reset, so 1, 2, 3, 4. Now we're out of reset. And let's get started. First is a load 0 into R0. Seems to have worked. There's nothing in there. Next up, there's a move from R0 into R1. A move from R1 into R2. Move from R2 into R3. R3 into R4. R4 into R5. And R5 into R6. Now we're doing a jump to a different address. That also seems to have worked. And now we're going to load the registers with just some arbitrary numbers. So first up is R0, which is going to get the hex value F0. Then R1 is going to get hex 55. R2 is going to get hex AA. R3 is going to get hex 0F. Then R4 is going to get hex 81. R5 is going to get hex 42. And finally, R6 is going to get hex FF, which is all bits set. Perfect, that seems to have worked as well. Now we're going to load the value 6 again into register 0, and then we're going to use it for the relative jump to jump over some knobs. So that's a 6 appearing here in R0. And then we're using R0, as you can see with the read enable light here, and we're using it as a relative jump offset. The light here indicates that we're doing a relative jump. And so if I hit the clock, indeed we are advancing by the value 6 in the program here. The next instruction is a load immediate of hex 40 into R0. So we should see this hex 40 being copied in here, which is the case. And then we're going to do an absolute jump to this address here, to this hex 40. So we expect to see this value being copied into the program counter, which is the case. And now we're back in this pattern loop again. And so what we're expecting to see is we expect all these registers being filled up with this walking bit pattern, but slightly different than we had in the first round. So first up, we set R0 to the first bit, and then the following instructions will basically set each of the register in turn. Pretty neat. So that's basically the bit pattern that we had before. Last time it was all in R0. Now we've spread it across the registers that we have. And now next up, we're going to do the reverse pattern. So this seems to be working. We're making use of all the new registers we have. And if I hit run, it's just going to execute this bit pattern loop here, and basically just going to go through all the registers we have in the register stack and load a value into them. All right, pretty cool. So we have 7 registers now that all seem to be working and that we can address from instructions and actually use properly. These will make writing software a lot easier because we have quite a few registers to choose from, and they make the processor a fair bit more powerful than just the measly 2 registers we had before. One thing we're not doing yet is actually making use of the third read port here on the registers. And I think that's something I want to tackle in the next episode. If you recall, the program counter here is actually a 16-bit counter. The absolute jumps that we can do, they accept the 16-bit value, but we're currently only using 8 bits for the absolute address. The upper bits are always set to 0. And the 8 bits, they come from the second read port of the register. And so I think what we want to do eventually is to have the third read port provide the upper 8 bits of the absolute jump address, such that we have the ability to jump around in the entire program. And this will require a few more addressing changes and a few more wiring things to figure out here. So I think that's something for the next episode. Can't wait to get that tackled. So thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.